This video will be a review of the statistical mechanics chapter of the chemical thermodynamics and kinetics playlist. So we start by looking at the Boltzmann factor and partition functions. The ergodic hypothesis is going to tell us that for any state with the same energy, we expect the same probability that our system is in that state. So that allows us to look at all these states with the same energy. But what about states with different energies? Well, that's where the Boltzmann factor comes in. The probability, the relative probability of being in each state is going to equal to the Boltzmann factor, which is e to the minus energy of that state divided by the Boltzmann constant times temperature. So lower energy states are more probable and higher energy states are less probable depending on their relative energies and the temperature of the system. But in order to get the absolute probability, we need to normalize this with this 1 over q, which is the sum of all the Boltzmann factors, such that these probabilities will add up to 1 or 100%. And this value is called the partition function. The partition function, or the sum of all the Boltzmann factors, is much like the wave function in quantum mechanics, the thing that tells us the state of the system with which we can use to measure all of the properties which you can know about the system. So one such example is energy, where the energy is a weighted average of all of the individual energies of each microstate. So the probability of being in each state is, of course, related to the Boltzmann factor and the partition function. You can also take the negative partial derivative of the log of the partition function with respect to 1 over kt if you have the partition function in a nice algebraic form. And if you don't, you just have a few states, it's sometimes easier just to do the weighted average calculation. So moving on to molecules, the energy of a given molecule is equal to 4 components: translations, moving through space; rotations, rotating around itself; vibrations, internal back and forth vibrating; and the electronic energy of the molecule. So each of these has their own partition function. For translations, it's 2 pi mkt over h squared to the 3/2 times the volume. For rotations, it's 1 over the symmetry number times t squared over each of the rotational temperatures, if you have a nonlinear polyatomic, square root of all that. For vibrations, you have a product of each of the individual normal modes of e to the minus vibrational temperature over 2t divided by 1 minus e to the minus vibrational temperature over t. Vibrational temperatures and rotational temperatures being specific properties in relation to the structure of each of those molecules. And the electronic partition function being the degeneracy of our ground state times e to the dissociation energy over kt. So the total molecular partition function is going to be the product of those 4. Q mol equals Q trans times Q rot times Q vib times Q elec.